So in this course, all right, we have done a lot of things, right? And, you know, we've been in the time domain. We've been in the frequency domain, right? And then we've been in the S domain. And yeah, every, you know, that might be, the step response to a low pass filter, which would be something like this in the S domain. The frequency domain is really when S equals J omega, right? And we also have, it's like frequency domain, but kind of like sum of cosines and sines. We could kind of put that under there as well, right? But when we're talking about a Bode plot, each point in frequency really is, just, so if this is F equals 1 kilohertz, right, and that's minus 3 dB, this is really telling us that, the magnitude will be minus 3 dB down. And if the input is a 1 kilohertz sine wave, I'm going to get a 1 kilohertz sine wave out, right? The magnitude would be minus, that's how I convert it back to real units, and there'll be a phase. So yeah, if this was first order, that minus 3 dB point would happen at a minus 45-degree phase, and so this would be the time domain equation, right? Now, yeah, the S domain, sometimes it's best just to look on the top down. We have the real, we have the imaginary. I mean, we have imaginary and the real, right? Which is great for putting roots. It's great for putting poles. Tried to show plotting this in 3 dimensions, right? But really, you can see what's going on right from here. And then when you want the Bode plot, right, well, you just find the magnitude and phase as we sweep J omega along this axis. But the Bode plot, right, it's a logarithmic progression on this, so you can't have negative numbers or real, right? So you're just, this bit here, right, calculating magnitude and phase is really just that bit there, right? The book doesn't seem to like Bode plots, and I think, I think it's kind of maybe a mathematical abhorrence, because, you can't have 0 hertz, you can't have DC, because, the log of 0 is undefined, right? And it doesn't show you the negative side, right? So we're just seeing this one corner, but man, I don't know of any electrical engineer that doesn't use Bode plots to show things, right? Because in our systems, right, I can plot our transfer function, and that's like a real key thing about this class is we stay in the S domain so much that sometimes, yeah, we forget what's going on in the time domain. But since we're here, we'll just write it out like this, right? That the zeta here is damping, right? Bigger than 1 over equal to 1 critical, less than 1 under, right? But imagine, if you will, I'm going to put a pole at a kilohertz and even at 100 kilohertz. Okay. So I'm going to have a break and then a break, right? So I'm in, oops, I got to get rid of that. That's a low pass filter, not a high. Sorry. So let's just call that 0 dB. Right, at 1 kilohertz, I start breaking. So I'm at minus 20 dB per decade. Then over here, it's minus 40 dB per decade. And I'm not showing the phase, but the phase would do, it would drop by minus 90 and then drop by another minus 90. Okay. So the thing is because this is a log of f, right, it's kind of easy to see every pole. All right. So I have 10K, I have 1K, 10K, 100K, right? Well, let's plot this non-logarithmically. I'm just going to call this 100K, right? So $10K, right? Now we're on a linear scale, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so 10K is here, all right? And so then that's 1K. Well, I don't even know if I can draw it. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So then 1K root is going to look like it's at 0. So I'm going to have this thing, it's going to come out almost undetectably. And no, now it's not even, it's going to look like this. And I can't even draw it. Okay. You've got to use these logarithmic things. That's what engineers do. All right. Now, yeah, and to imagine trying to do the system ID, right? Ugh, that's ugly. That's even uglier. So this is minus j omega plus j omega. What I'm trying to do is draw Butterworth second order filter. Okay, so I can tell it's low pass because it's, you know, high here and goes low there. All right. But, and I guess if I looked at the phase, I could see that it would be a minus 180, but you know, I can't really tell what's going on here, right? If I'm just to jump into a system ID, right? If I come out, right? hey, F naught is where the phase, or omega naught, right, is where the phase is minus 90. I just look up, then go over here. Let's say it was minus 3 dB. I get my gain DC from here, which is 0 dB, let's say. Right, I calculate that. I have the gain at omega naught, which it's easy to read off because this is on a logarithmic scale, right? So I have gain at S equals J omega naught. So with this and this, all right, I find what frequency gives me minus 90? That gives me omega naught. All right, what does omega naught gives me? It gives me a place to read off the gain. I read off the gain at the low frequency, so I have omega naught, the omega naught frequency, and the low frequency gain. With those three things, I can backfit this equation very easily. Okay? Imagine this not being on a logarithmic scale. It'd be pretty hard, all right, to see what's going on. All right? So, but we did start off the semester. We did start off in the time domain, right? Right. And I would make up waveforms for you to try to break down. Okay. And really, even though there's other, we talked about UT, the ramp, and delta T, right? Because these really, now sure, there's sine omega T, right? But, and there's E to the minus T, it's just called, something like that, right? But really, we tended to try to break these down into things like this because, yeah, the integrals are easy, right? Hey, the integral of a constant is a linear. The integral of a ramp is what? T squared divided by this. And yeah, that integral of the delta function, it was really, we use that more for sampling. Like, what is the value at that moment in time, right? But we tended to break everything up, right? So, this might be UT minus UT minus 1. That was like a classic one. Here I'd have an RT, right? It goes down, right? So if I'm up at 1, yeah, I got to subtract that. But not only does it go down, but it stays minus UT minus 1, right? Not only does it go down, but it flattens out. So I have to subtract that. Now here, yeah, I kind of have RT, then it's UT minus 1, because it goes down by 1, or maybe, well, that's 1, if that's 2, or if that's minus 1, and that's plus 1, yeah, then it's like 2, because it went down by 2 units. But I didn't flatten it out, so it keeps going back up. So then I got to subtract it again. But now I'm at, minus, let's say 2. And then it goes down, but it's climbing back up. So let's see, 1 drop, 2 drop, 3 drop, and then let's call this point 1, 2, 3, 3.5, RT minus 3.5, right? Because it's going up and then it flattens out. So I had to get rid of the slope. All right. And yeah, there's, some of these classic shapes that you see crop up again and again, right? Where, oh, I have an RT. Now at this point, I'm going down. Well, that's twice the slope. So I have to, right? Okay, I'm going down, but now I'm flattening out. No, that's 2, right? Now, why were we doing that, right? Well, because not like I said, I gave you a hint. The integrals are easy. Well, what is the Laplace transform but an integral? Right? So ramps, linears, steps, all that. Hey, it's easy, right? That goes to 1 over s. RT goes over 1 over s squared, and then, and so on. All right, well, that's great. Who cares? Well, the thing is if I want to know if I have a step response and I feed that into a system, right, with an impulse response, which would be h of t, right, the output is this u of t convolved with h of t, which involves integration, which, yeah, for the first order low pass filters and things like that, it's pretty easy. But with the Laplace transform, the Laplace of u of t just becomes 1 over s. The Laplace of h of t becomes h of s. And then to find out the output, that's multiply, not convolution. Sure, you got to take the Laplace transform, multiply it, and then manipulate the algebra to get the inverse Laplace transform, right? But you take the Laplace, multiply, you do some algebra, you take the inverse. And that rather right, rather than going through this convolution integral. Now, if it's so easy, why do it? And that is because you need to intuitively understand what's going on. Because here is here's an input, right? So that's RT minus 2, RT minus 1. Let's call that 1, 2. That flattens it out. Minus, we want one slope down, RT minus 2. Then we want to flatten it back up. RT minus 3. So we have 1, 2, 3 items, right? Well, what are we convolving it with? Well, if we convolve it with this shape, 1 bend, 2 bends, 3, 4, right? So I'm going to multiply 4 things times 4 things, then take the inverse, and then take the inverse Laplace transform. You just might get lost in the shuffle, right? Even if you were going to convolve this with a decaying exponential, right? The chances to kind of mess that up are high. But yeah, you would just look at it and say, all right, because it's not enough just to manipulate the algebra. It's very algorithmic. Almost everybody gets that right. Can you plot it? And I'm like, well, I'm going to have a region where I got a linear times a linear. That's going to integrate. Then this is going to, at some point, the area is going to flatten out because this is completely inside of this, right? Then it'll go on for some time. But they both start and end at 0. So it's going to start and end at 0, right? If I have a ramp convolve with this, right? Well, this is going to keep increasing, right? This might go up and, this might go off and on, but this multiplied by this will just keep getting bigger. It never goes back down, right? And then there's things like the delta function, right? Infinitely high, infinitely short, a little bit hard to do in lab, right? But I can kind of approximate it. Right? If this width is so much thinner than the width of this, it'll start to approach a delta function. So if you want to, and here's the thing, I put a rectangle in here. I could put a thin triangle. I could put a very thin exponential decay. At some point, it doesn't matter as long as you're a lot thinner than the system. So if you've taken 112 or you're taking 112, right, Professor Santa Cruz has this example of, I don't know, you're in a stadium, here's all the seats, right? And he wants to get the impulse response of the system of the stadium. So he puts a balloon there, it pops, right? You get the echo, right? I'm just going to make up this system response, right? This is HT that he measures. He digitizes it, puts it in a program, and then you put in music. Yep, you convolve with that HT that you measured, and then you get what it's like to be in a stadium. How does that work? Was that an impulse response, infinitely high, infinitely short when you pop that balloon? No, but look at the kind of what you might call the time constant of the stadium, and a pop and a stadium, yeah, I mean, the time constant would be a lot shorter of, the time that balloon is popping is a lot less than it takes to propagate, right? So yeah. Now, is the area under that sound of popping curve 1? No, of course not. But it doesn't matter, right? Because if the amplitude is reduced, well, you just multiply it by gain till you can hear it, right? They don't actually care, right? So if we had, I'm sorry if I'm drawing this in electrical terms, right? We have 1/4 of a car, right? All right, we got the damper, we got the inductor, they're in parallel, and we kind of want to test this, right? Sure, we could have it go over a step, then we'd get the step response, and then we could take the derivative. But, we could have it go over, and you might say, well, no, do an impulse response. Okay. Anyway, this looks kind of bad, doesn't it? I know what happens when I drive over a curb. I blow the tire. I got to buy a new tire, right? But think about it. Let's say I have a speed bump, right? And and I'm giving it a time constant instead of a distance because I'm going at a certain speed, right? So, for constant velocity, the bigger this hump, the larger the time constant, right? And then maybe this system, right, it's an RLC. Let's see, what would that look like? Right. Well, if I can keep this time constant of the speed bump smaller than the time constant of this, it doesn't matter that it's not infinitely high. It doesn't matter if the shape is curved out. You're going to get that impulse response, right? If you have a mass swinging back and forth, right, and you want to get the impulse response, well, probably you just need to hit it with a hammer. Boom. And then it'll go. Right? And it'll start oscillating back and forth. Right? As long as, but if I pushed it with a hammer so slowly that it's on the order of the time constant of that mass system, well, then it's not going to work. Right? I'm getting like maybe a ramp response, but a sharp tap, right? I don't know. This isn't a very good. I'm not an artist, right? But you're driving, right? You want to get the time constant of the impulse response of your car. Well, you just jerk the wheel a little bit, right? And you should be able to measure the response of the car. But if you go really slowly, well, that's probably going to be more like a ramp response. But yeah, if I jerk it, that's step. If I wiggle it back and forth, that would be impulse, right? Now the thing is we spent a lot of time just with these two things, right? We had low, we had high, right? And, right, we have 1 minus e to the minus t. We have e to the minus t for step, right? For, right, that's what we get for the step. That's because for the low pass, we're getting this for the transfer function. For the high pass, we're getting this. The step is 1 over s, 1 over s. Right, this has a Bode plot, right? It has a phase, 0 to minus 90, because it's just first order. That would be the minus 3 dB part, right? When s is 0, these two cancel, you get a gain of 1, which is 0 dB. Right here, as s goes to 0, the output goes to 0. Right, then at some point, s is bigger than omega naught, and it evens out, and the phase goes from 90 down to 0. Right? Those are the transfer functions. Now that I multiply this out, oh, well, what is the time domain? All right, you just look that up off of the chart. The s's cancel, and you would get either, yeah, the omega naught would be there, right? So notice that decaying exponential is everywhere you go. All right. So yeah, put that into an op amp and see how it changes it, right? But it'll just, it could invert the gain, it could make the gain bigger, it could buffer it. But yeah, this kind of, plot, but linking finding a transfer function, plotting the transfer function, magnitude and phase, finding the inverse Laplace. Oh yeah, then you got to plot it, right? I forgot to plot it, right? So this is first order, right? Takes me about 5 tau to go from 0 to 1. Here, right, it takes about 5 tau to go close to 0 from 1 down to 0, right? That's like an interview question, right? That you will see that on the final, right? But 2, these are just simple steps. Sometimes I put in these kinds of waveforms, right? Hey, what is this going to look like if I put it through a low pass? What is it going to look like if I put it through a high pass? Right? One, the low pass kind of blurs edges, takes away the corners a little bit, right? The high pass, like ultimately, passes the derivative. If it's no derivative, it goes to 0, right? Here, then it goes down, and goes down again, right? Edges, sharpens, blurs, right? But what if I had this is ht, e to the minus t, right? And then I had this one. Then I had that one. So I've got a constant that's making this take longer and longer. If I convolve this with a sharp thing, it's not going to blur the edges much. In fact, the smaller this gets, it's going to get like an impulse function. The more it goes this way, yeah, the more it will blur the edges, right? And so I have some, I think, some notes and videos on that to, you get a shape, kind of intuitively show what's going on with that shape. All right. Now, yeah, we did a lot of plotting and deriving of these, right? But then we got into this thing about feedback where we would have a summer, we would have a transfer function, then we would have some kind of feedback network. All right. Now here's the thing. Depending, right, many times they'll take this as V out, but in our DF2, we can be taking V out almost anywhere, right? Almost off of any node. This is showing that it all flows one way. The DF2, that feedback network is happening in parallel, and then sometimes you have a feed forward network that things can happen in parallel, right? But that negative feedback allows complex poles, right? These circuits, right, I could take this and feed it into this, right? This has got a real pole, this has got a real pole, right? I multiply them together and I get a real pole, two real poles. And that's the other thing about the Laplace transform is that to try to do this in the time domain where I'm trying to write an integral and then that gets fed into some other integral circuit, no. You take the Laplace transform and you just multiply stages as they go through, right? It'd be pretty hard, right? I can take this. Okay. I have a high pass, a low pass, and a high pass. This has a real pole, that has a real pole. When I sum them, right, how do you find, let's say this gives me omega 2, this gives me omega 1, right? So I have the high pass and the low pass. How do I combine these? Well, right, I multiply this by s plus omega 1 divided by s plus omega 1, and I cross multiply over here. Well, anyway, you're just multiplying real roots. So this can't be complex unless I had an RLC circuit over here. So really, without negative feedback, the only way you can get a negative root, I mean a complex root, is with an RLC circuit. But with negative feedback and op-amp circuits, you can get real roots. Now, let's see. This would be a generic differential equation transfer where I have a numerator and a denominator, right? Which can be implemented in an op-amp-based circuit, right? The first thing to do, you find the highest order and you multiply through by that to get it all. These are all derivatives, S squared, S, right? Those are derivative circuits, very noisy. We need to put them in to, especially this would be a double derivative, right? That'd be very noisy. So we multiply everything through by this to get integrative circuits. Okay. The whole point of DF2 is to share the integrators. Okay. Now here, there was a B naught. It gets added. There was a B1 because it goes through one integrator and that gets added. And then we have a B2 and that goes through and that gets added. And then we have an out. Now, yeah, if there's no B naught and no B2, well, B1 comes right out. If these two are missing, well, then it comes right out from there, right? But notice, these are parallel circuits, right? So B1 is just some constant, B1, right? This is B1 over S. This is B2 over S squared, right? So I'm not drawing the op-amp implementation, but these are all in parallel, right? So when they say, oh, are we going to do parallel? Yeah, because DF2 has parallel. Not only that, notice these are in parallel as well, right? A1 and A2 are in parallel, okay? But yeah, the whole thing is DF2. That one is pretty algorithmic. You just got to make sure, yeah, take the output off of the right place, make sure it's inverted or not inverted. Don't, yeah, just kind of follow the procedure. All right. Now, yeah, some other things that we did with op amps is that in the past, we've just said, oh, the open loop gain is infinity, Rn equals infinity, and then we derive some things. But no, a vol at the simplest level is like gain bandwidth like this, which All right. So this is my positive pin. That is my negative pin. This is out. Before, this was just something that went to infinity. Right? Well, now, hey, how would I draw that negative feedback? Here. Which, what would that be? Well, it's our buffer just drawn upside down. Okay. Bless you. Well, now we use our, I call it the feedback methodology method, right? Now, here's the thing. Yes, HS is this thing here, and HS is here. No, just take this HS and draw it out the way I showed you. I'm telling you. Because the denominator of HS is going to be there no matter what because of the 1. So I'm going to have S. The denominator of HS is going to be canceled out in the second term because it appears in the denominator of the second term. So I'm going to have GS 2 pi gain bandwidth, 2 pi gain bandwidth. Now in this case, what is the transfer function back? Well, V out equals V in minus. It's 1. All right. 2 pi now, hey, when will this act like a buffer? Well, S equals J omega. If omega were 0, right, at DC, this would drop out. 2 pi gain bandwidth divided by 2 pi gain bandwidth, it'd be acting like a perfect buffer, right? But really, all you got to do is, well, the magnitude of S, and you can do much, much less than that or just less than, right? When that happens, these two cancel out. Now, it's true, we can be a little more specific because the magnitude, right, equals 2 pi gain bandwidth divided by the square root. What's the real part of that? The imaginary part of j omega? It's omega squared. This 2 pi gain bandwidth, right? So really, squared. This squared has to be bigger than this squared. Then it cancels out. But you're effectively getting the same thing, right? But really, if you get a data sheet and you read off the open loop gain, right, you'll get some big number here. They'll tell you the gain bandwidth on the data sheet, and you get a number there. And yeah, you can't really plot 0, but you could 1.1 hertz is effectively 0, right? Draw a line through it, and you can safely act like an ideal op amp here, right? Now it's true, sometimes you have a second order op amp. And really, there's so many capacitors in there. You can have 7th, 8th, right? But as long as the gain bandwidth is a lot smaller than all those other ones, right? Oh, you can have a second order. And depending on, you need to add the open loop gain back here, because at 0, that drops out, right? So depending, right, on your choice of AV, on this, right, in here, when I put that in the feedback loop, something that was overdamped, because yeah, look, there's one root here, and there's one root at 1 and one root at 1 megahertz. Those roots are, those poles are separated by quite a bit, right? It's really overdamped. In fact, it's practically, I mean, if you look at it, if this is 1 hertz and this is 1 megahertz, it's like it is first order until a tenth of this, right? So remember that first model where we use, it's just the gain bandwidth divided by S? Well, when these are separated by such a large distance that, yeah, could be. In a lot of cases, you can interpret it as first order. However, if you do a step response of your thing and it starts to ring, hey, that's second order. There's something else going on, right? And so we have questions. Is it overdamped? Is it still underdamped? Is it critically damped? Is it going to ring, right? There's all these kinds of questions that we can ask. That step response, right, it is easy, right? But it does have 1 over S, meaning it's got all those frequencies in it. And then what if we talked about testing with a impulse, right? A delta function is 1, meaning it has every frequency. So when you test with a step function, right, and you say, well, my circuit's going to stay in here. I put in a step or I put in a delta function. No, I'm going to get, so the step will go down like that, but the delta function will have a constant frequency everywhere, right? Now, our op-amp circuits can ring, right? Severe ringing, people would call unstable, right? Engineers would call unstable. Mathematically, though, right, if I have a pole at, I have the real part plus j omega, the real part has to be less than 0, right? Right. But if I'm really so close to the imaginary axis that I can't tell, it's effectively unstable. I'm not going to trick you on the exam. It'll be stable, or, use this definition, right? Let's say we have something. We have an HS that, yeah, it has positive poles. Sorry. Right? It has a positive pole. Or, it's got poles on them. Right? It's got poles here, or it's got poles here. It can be complex. They're there, right? Okay. Can you come up with a GS that makes it stable? And we talked about several GSs, right? We have proportional, which is just a constant, right? We have proportional plus derivative. Okay. Now, yeah, you can just have derivative too. Why is it called derivative? Because, it's in the numerator. That's a derivative. We have proportional plus integral. All right. Those are the three ones. There's more, but those are the three. And so you're going to have a transfer function. And let's say it's omega naught S minus omega naught. Where's the root? At positive omega naught. So this is unstable. All right. So I put that in my equation, omega naught S minus omega naught 1 plus my GS omega naught S minus omega naught. I don't know, I haven't said what that is yet. All right. Well, that pole is repeated, or I don't want to use the phrase repeated, but it's right there because of the 1. So we get omega naught. We get S minus omega naught. We multiply through, and this drops out. So we have plus GS omega naught. All right. Why is this unstable? Because this was less than 0. It was negative, so that when you find the root of that, the denominator, right, it's on the real side. So I got to make this positive. All right. If I have K times omega naught, well, if K equals 1, then I get omega naught minus omega naught, and then I just have this, which is an integrator, which is in fact unstable. So I just have to make K big enough to make this non-negative anymore. That's it, right? But let's just modify it. What if I said, no, we just have proportional times derivative. All right, I have S minus omega naught plus KS omega naught, right? This is still negative. Oh, I've added an S, great. But even if I make K negative, there's still a sign change. This is positive, then this would go negative. From Descartes' rule, it's just not going to work, right? So, yeah, the only thing that's going to work is proportional. But sometimes, right, let's say you have an omega naught squared. You have S squared plus omega naught squared. All right. That S term is missing, right? You need a GS that adds in an S. Well, what's the only thing that'll be, what's the only thing that'll do that? Well, some kind of derivative feedback, because this derivative times omega naught will put it right there. And in fact, whatever that K is, you can set over, under, and critical damped. All right. So the question is can you make it stable with this? You don't have to say, oh, this is, these are the new roots. But yeah, you know, in this case, yeah, K omega naught has to be greater than omega naught, right? Then, now, yeah, it can be 1 point, 1 + 1 nano times omega naught. Yeah, is that greater than it? Yeah. But from an engineering standpoint, it's not, right? But really, you just would have to say something like that, okay? 132, you're going to get into it a whole lot more detail, all right? And then I think really, here's my thing about the second order, right? Is that what would be a third order? I'm just gonna give a number A, right? A third order would be a second order times the first order. What would be a fourth order? Okay. And what would be a fifth? Oh, well, then I'd have another one out here, right? So you can break everything up into first order and second. So you've really got to understand these two, right? And what does a second order filter look like? You know, it's got over under critically damped. And notice I haven't put in this part here, right? Because really, omega naught squared, low pass. S omega naught, band. S squared, high. Low plus high, notch. So really this whole course, we're going between the time domain and the frequency domain. Now, yeah, S is complex, right? You could call it S domain, and then S equals J omega is in fact the frequency domain, right? But going back and forth and breaking signals up into simple things so that we can work on them in the Laplace transform, go back and forth. Now, yeah, this S equals J omega is the Fourier transform, right? But the Fourier expansion, right, is sum of never ending sine, cosine. And this, right, the Fourier coefficient expansion of a waveform, of a sine wave, right? That really means that that sine wave has been going on for all time. When we do our project in pulse width modulation, this isn't ut minus 1, because that goes up and comes down and then nothing changes. No, it's been a square wave forever in the past and forever in the future, right? But where does the Fourier transform come in? If t, the period, gets to be a lot longer than like how long you're on, yeah, you eventually go to the Fourier transform right? Which is a special case of the Laplace. All right. I haven't really mentioned too much about those coefficients because on every exam, you know, people do really well on that. All right. I don't have to worry about it too much. But really, I don't know how to say it, but you are now in the club, right? There's things that you now know, like, now, yeah, other people would have seen Laplace transform, but the things you know now, right, separate you from the other engineering majors. And yeah, they separate you from everybody else. My brother, he just loves to make fun of imaginary numbers every time we get together. He's a lawyer, and it's like, yep. And that imaginary number, right, allows us to go from the time domain to the frequency domain where life is a lot easier. Okay? Artem. Okay, so, well, no, let's see. Artem. I'm going to repeat what Artem. So I can basically, when my brother says imaginary number or something, and I'll say, my imaginary number has a real application. And see, we're all laughing in the room. Right there, boom. Nobody but people who've had a 110 type class, you know, all would get the joke. It'd be like, huh? What do you mean real? What? Okay, no. And not that, you know, lawyers are stupid, but yes, I try to say laws. Yeah, the law is like justice doesn't exist, right? It's a concept. I like justice, right? I like things to be fair, but you know, sometimes as I try to tell my colleagues, we have a lot of rules in the university, but you know, they're not the laws of physics. They can be broken or modified if we think that they're no good. Now, here's the thing. Sometimes we harp on lawyers, right? Because there's some law and it doesn't make any sense, or you just hire somebody to argue your case and it's like money versus money. Okay, right? Here's the alternative. Sword versus sword, gun versus gun, war, right? We settle things, you know, let's say, you know, Devin and I have a disagreement about something. How do we find out who's right? Well, logically, oh, Devin made a better logical argument and Professor Parent pulled it out of his behind. No. We fight each other, and whoever wins must be right, because how could you win without God's blessing if God is all powerful? So therefore, how could you be king without God's blessing? Makes no sense. I'm just saying the law, we just, yes. Maybe, you know, we don't like it, but it is certainly better than the alternative. All right. And yes, his jokes are made with love. So anyway, I think we're running a little bit out of time. Email me your questions up until the exam. All right.